in his personal stuff. And so that's a picture of me and my kids in the cockpit of the orbiter looking out at the space station wing. So it's just a tremendous opportunity to get to work with folks like this. Now, as I was starting my career, trying to figure out the things that I wanted to do, this was after I got my biomechanical engineering degree. I went back and worked on biomedical payloads for the space station. This is a refrigerated centrifuge that they're testing out right before we fly it up to the space station. One of the things about testing, right, is trying to make sure that the designs that the engineers come up with are actually going to work. And in this case, they forgot to design in restraints for the test tubes in that refrigerated centrifuge. So I pivoted from 7 years as a flight controller working space shuttle missions. Then I went back to school and I got my PhD. I already had a family at the time, so that was a little bit different type of challenge. But I will tell you, I focused because of that, and so I got through that PhD program in about 2.5 years, and then went back to work, working on the space station payloads, like I said. And it was after that that I got the offer to then join NASA permanently as a civil servant. And so from there, I moved into a couple of other roles where I worked in our safety and mission assurance organization. I worked shuttle upgrades, did a few things like that. And then we had Columbia happened. And I'll tell you, so those were 7 friends of mine that were on that vehicle. And it's all part of what I was having a discussion earlier about risk, right? And we'll talk more about that and how to manage risk, how to understand what risk is out there. For us, daily job is trying to make sure we're doing things that are going to keep our crew safe, right? So it's a fundamental mentality that we have. But it still requires all of the development. You have to have the basic understanding of engineering, science, all the disciplines, because not just technical, right? In order to fly, we've got to have budget management, right? We got to have all the different things that you need, contract management, but all of it requires an assessment of risk. So I went through that whole process to where I was at the time. Actually ended up leading the team that did the retirement planning for the space shuttle program as it went away. Then we move into another phase of my career. So that's already a variety of roles that I had in the first 10 years or so of my career. But then we moved into, all right, how are we going to go do exploration? So this is a question that I ask really all the time. What are the capabilities we need to do future deep space human exploration? There's a variety of capabilities really that we need to develop. This is just a subset of those capabilities, right? We need to have habitation. We need to keep people alive wherever we go. So you need environmental control and life support capabilities. You need transportation capabilities to get there. So you need propulsion. You need whatever those transportation capabilities are, all the different types of propulsion, right? You need to be able to, the deeper you go, you need to be able to operate autonomously. So these are all different aspects of technologies that we continue to try to advance in order to explore further and further into deep space. Fortunately, I've been able to work on a number of different projects that actually help advance those capabilities. So, any of you who've seen The Martian, read the book? I'm seeing a lot of nods, not a lot of hands, but a lot of nods. So that's all right. So you know it, right? But you think about it. The reason I ask is because the vision, right? When Mark Watney's there on Mars, and you've got the habitat and the lab and the rover and everything is right next to each other. Right? Well, when we landed, the rovers that are on Mars today, right? They landed within a landing zone of several hundred kilometers. Just pick a flat spot that's known from the imaging we've done, and anywhere in there is acceptable. right? So you go land there, but think about where Mark Watney was, right? And you want to land the habitat several hundred kilometers away from the lab, which is several hundred kilometers away from the rover. Now you got to figure out how to land those things all next to each other. So looking at autonomous precision landing was a key technology that we needed to pursue. Autonomous meaning the vehicle is making the decisions itself on where to land, right? Obviously you give it the guidance, but if you're going to go land on Mars, which is pretty similar to the moon, what differences? What's different? No atmosphere. That's right. So you got no parachute, right? No heat shield needed. But the trajectory is roughly the same anyway. You're going to do terrain relative navigation as you approach your landing site. But what we needed to focus on was one, improving that terrain relative navigation where we could really pinpoint where we were trying to land, but then also figure out where all the other obstacles were on the surface and avoid them, right? But still land close to where we wanted to land. So we came up with a project that would allow us to advance that type of capability. It's called the Morpheus Project. I don't know if any of you happen to hear of it. We stopped flying back in end of 2014. But we created the Morpheus Project, right? So the whole idea was to advance these technologies. Morpheus was an Earth-based terrestrial lander, but rocket propelled. So we actually, the other technology we were pursuing was liquid oxygen, liquid methane propulsion. Hadn't been done before. There'd been testing with engines on test stands, but that was it. No one was actually pursuing methane propulsion now. Does anyone know if it's being pursued elsewise these days? SpaceX, right? Starship, those are all LOX methane. The Blue Origin, that's all LOX methane. But we did this 15 years ago to pursue advancing that capability and demonstrate that LOX methane would actually be a viable propulsion capability for future landers. We brought it to Stennis Space Center to test engines, things like that. And then these companies came on afterwards and built on those technologies. But again, so we were demonstrating that propulsion capability, and we were demonstrating that autonomous precision landing capability. So we weren't really focused so much on the structure of the vehicle. It had to survive, right? We weren't so much focused on the avionics. It had to just allow us to fly. We were focused on the software, because that's where the autonomous precision landing, we had the instruments and the software. So we had software built on this lander that acted as though it was going to be landing on the moon. Right? And so it was navigating with those inputs as though it was going to be landing on the moon. So no use of GPS, no use of any of those other assets that are available here on Earth. So we went out and we said, we're going to go build this and we're going to go advance these technologies. We had a small group, about 40 NASA civil servants, did this in-house, so hands-on design and build of it. All the parts of this, the frame, the tanks, the engines, had our own welder welding the engine, so we did all in-house development of this with those 40 people. And in 7 months, we went from the concept to ready to actually test. Now this is actually out where the new A&M center at JSC will be. So it's actually going to sit right on top of where we did this testing. So I got to get out there before the ground breaking and put a stamp down there or something of this activity. But this is where we were testing. And so we spent 7 months putting this vehicle together. We had done one test prior to this where all we did was ignite the engine. We did not increase the thrust of it and didn't try to fly it. Just wanted to make sure we could ignite the engine. Now, why are we hanging from a crane? Anyone, any idea? Just in case. So there's a school about 2,000 feet this way. All right, so it's for safety. We had a problem with this rocket-powered lander. We didn't want it landing on people, right? So we lift off the crane, and so this is our second test. That's not supposed to happen. Any ideas what happened? Any thoughts? Improper fuel mixture. No? Good thought, but no? Not the LiDAR. So the LiDAR we would use to scan the surface, but you're heading in the right direction, yep? Sorry? Yep. Yep. So our inertial measurement unit, which basically has our gyroscopes, right? So the way it actually didn't fail, we were a small project doing research and development. We were borrowing hardware from folks to be able to make this work. So we actually borrowed it's called an inertial measurement unit, right? It's a sophisticated gyro that is used for a space station. We borrowed a test unit from the space station program to put on our vehicle. When they gave it to us, they forgot to give us an addendum. The addendum to that said the gyros were rotated 90 degrees. So we didn't have that in our software, right? But we did have a second problem. We had a failure when we sent the ignition command, the throttle failed full open. That's why it didn't shut down for as long as it did. We had an electronic component that failed, that fried on command, and so that throttle failed full open, 100%. Right, and it took 11 seconds for the guy all the way down at the end of that road to hit the safety button and turn off the engine from firing. Right? If it wasn't for that addendum problem, we wouldn't have spun, and instead we would have gone straight up through the crane. So we got lucky. 5 days later, we had all that fixed, and we flew again without problem. So we spent 2 years building out, testing, demonstrating that this vehicle could work. And then we went out to Kennedy Space Center because, again, we wanted to fly without the crane. We had too many things around us to fly in Houston. So we went out to the shuttle landing facility. So right at the end of the shuttle runway, we built a moonscape, 100 meter by 100 meter moonscape, and our own launch pad. And we went out there to go test. So this was the second test flight that we did there. The first one we ignited, we barely lifted off of the ground, and we had an engine burn through sensor failure, caused the engine to shut off, and we just settled right back down. So this was 2 days later. Of work. This view shows it a little bit differently as well. So, tried to abort, because that was the only command that we had. Yeah, that's loud. So again, after 2 years, this is the only one we've got. What do you think happened? Any guesses? Any guesses? No puppies were harmed in the making of this film. All right, if someone guesses, they're going to get some swag. Not the LiDAR. LiDAR, go ahead. It was the gyro again. It was the gyro again. However, this time, the gyro, it's always the best part. I can say that now. I couldn't say it back then. So the gyro, the IMU sitting up on top of the vehicle, right? When we lit the engine, on that concrete pad, the vibrations caused by that engine thrust came back up through the middle of the vehicle and caused the cable connector to the gyro to fail, right 0.6 of a second after liftoff. So when that happened, there was no longer commands or information going to the computer, so the computer just kept correcting for the last known error and flew a parabolic trajectory right into the ground. Right? So that's what happened with that. Now, we were, that was 4 days after Perseverance landed on Mars, I believe, right? 4 days after. So that was the leading story on NBC Nightly News that night, and we were second. Because we broadcast these tests live over the internet back then, right? Just showing that development. So we did that, but after that happened, we gathered everyone around, we picked everything up, we said, let's go figure out how to do this. So we spent another 7 months making 70 changes to the vehicle, doing those updates, still sticking with a lot of the same risk posture that we had before, only making changes in specific areas. So we added a second IMU as an example, right? But it's still only single engine, still only one throttle valve, right? You can still have single failures that cause the vehicle to crash. So we really didn't change the overall risk posture, but we looked at the areas that we needed to make updates. And you can see in some of these videos, you can see we also built a flame trench so we could direct that vibration energy away from the vehicle. And we ran test after test after test under the crane until we got confident that we could fly this at KSC again. We upgraded our control center out of KSC. And then we did flight after flight there, continually increasing our capabilities, the distance we could fly, the altitude we could go to. Some of these views, I show it just because it brings me chills every time I show it. So I think they're pretty fantastic. Like this rising over the shuttle landing facility, and you can see the vehicle assembly building in the background. I just think that was fabulous. And it was at a time when we weren't flying. Shuttles had already retired. We were waiting for the next thing. And so we were the only thing flying out in Florida at that time. This is the LiDAR that we would operate as part of that hazard avoidance. It would take 4 seconds to scan this entire lunarscape down here. 4 seconds to scan it. Another 6 seconds for the vehicle to process where then it wanted to land. And so it would autonomously decide where to land. We had boundaries that if it exceeded those boundaries, we would simply hit a button and shut off the engine and allow it to crash, right? Because we wouldn't put anything at risk. But that was the only commanding we had of that vehicle once we told it to ignite. That was all we had. It did the rest of the flight itself. Then we also had to do it at night. Demonstrate that all of those sensors would work as though they were landing on some extraterrestrial body, right? So all of this was those same 40 people doing all of the different aspects, designing the vehicle, building the vehicle, controlling the vehicle, writing all the procedures, doing all the software, filling the vehicle with propellant, all of those aspects. But we had interns down at the landing site to take these pictures. Not really. But we did have about 75 interns that worked on this project over the 4 years that worked on it. So we definitely brought interns through. We definitely felt like we were lucky to be able to work on a project like this. So we built a following in what we were doing here. But those 40 people really learned what it was to manage risk, how you go deal with where to apply redundancy, where reliability matters, right? How to manage risk there in a project like that, where you don't have people that are on it, but you put the safeguards in to make sure that people don't become a part of the equation, even on the ground, right? So that was a key part of that. But then you tell your story. So we had pieces of Morpheus that were in the Smithsonian Air and Space up in DC. If you ever go to Space Center Houston, the Morpheus vehicle that was in all those pictures is hanging from the ceiling down there. So you can see it there. And then you also recruit others to help tell that story. So at the time, we wanted to make that a big deal. So that's Andy Weir came out and joined us for what we were doing there. He spent about 3 hours with us, understanding all what Morpheus was. I loved the flying under the vehicle and explaining the engine to him while we were there. So they'll always tell that story. But so that's kind of the R&D side of building out capabilities. Now you get to, okay, now we want to actually take those things and be able to go execute human missions. Right? Yes.
I have one question. When you test such vehicles and when it fails, it explodes. There could have been 1,000 things that went wrong. So how do you point out exactly what went wrong after all that mess and explosion?
So great question. Great question. It depends on what data you're able to collect, right? It's the forensics associated with that. So we were very fortunate in a couple of different ways, right? One, we had our avionics box, our computer, sat on a shelf off to the side in the corner of the vehicle, the way it was designed, right? So it actually, even though it did burn a significant amount, it fell away from the vehicle to an extent, and so we were able to recover the hard drive, essentially, right? So we could pull the high rate data. So we still got back in the control center. We got everything that was sent to us, right? So we had all of that data. But the high rate data, the vibration data in particular, right? We were able to pull that data and be able to show where the vibration increased on the vehicle, right? Through the accelerometers that we had on the vehicle. So we could actually go back and do the forensics to understand that. And the other thing that's after the crash, right, that I didn't point out. So you saw that explosion, you saw the fire associated with that. You wouldn't think we'd be able to reuse anything from that vehicle, right? But there's a part that we were able to reuse. Any guess what part we were able to reuse? Not the gyroscope. Great thought, though. Great thought. Great thought. What part were we able to reuse? Not the LiDAR. In the back? I'm sorry, I couldn't hear you. Not the tanks where the gas was held. Nope. The engine. We were able to reuse the engine. All right, now why were we able to reuse the engine? So not because they were both able, it was good thought, but not because they were able to withstand high pressure, high temperatures and pressures. It's actually because they could withstand cold ones. Because we were using liquid oxygen and liquid methane, both down at the negative 250-ish degree Fahrenheit temperature range. And when we crashed upside down, we kept flowing fuel because it was all pressurized. So fuel kept flowing through the valves, through the throttle valve, through the engine. So it actually stayed cold while the explosion and fire were happening. So we were able to use the exact same injector, and all of the future flights that you saw were with that exact same injector. So we did not have to rebuild it. So anyway, so we talked about improving technology. So we took the experience from Morpheus there, and there was, at that time, we're trying to build out the Orion capability. Y'all know what Orion is, right? So a key part of Orion is the launch abort system. The ability to save the crew if there's a problem going uphill with the SLS rocket, right? key capability that Orion needs. Well, they were really working to try to build the Orion capsule itself. We needed to execute a test of that launch abort system, and to not distract the team that was actually building the flight vehicle that was going to fly, we brought that need in-house. So the same team that did Morpheus, much of that same team, then was tasked with actually building a crew module that would mimic the Orion to the millisecond in order to execute a full-up test of the launch abort system and demonstrate that it would save the crew if we had a problem in flight, right? So that was my next project to lead, was to take that team, change what they were doing, and we went from a very complex, that lander, as simple as it might have looked structurally, very complex to fly the way we flew, and all the autonomous precision landing, all of those things, very complex, but with a lot less overhead programmatically. I could run the whole thing and do it all myself, right, because it was research and development. To now working with Orion, the capsule, and building that all out and mimicking Orion actually was less complex than what we did with the lander technically. But it was more complex to deal with Lockheed Martin as a provider. Not that they're bad, it's just you're dealing with another entity, dealing with the Orion program and their development work, right? Northrop Grumman and the launch abort system, the rocket that we had to build to put this on. So interfacing with a lot of other entities to put the whole thing together added complexity in a different way. But we still took the same team, and our intent here was to be able to fly. It's just a three-minute flight, right? But we had to go build all the different pieces of that. We had to do it as quickly as we could so that we could demonstrate, again, for the crew, that they'd be safe when we were ready to go fly Artemis II with crew on it. So we went through that process out at Langley Space Center, in Langley Research Center, in Virginia. They did the build of the structure, shipped it down to JSC, and we did all the outfitting, all of the cabling. We had 11 miles of harnesses on that vehicle with all the instrumentation that we had to put on it. So building out all the computers, all the software associated with it, again, down to the millisecond. Did all of that work in Houston. Still a lot of hands-on work. We didn't contract out with someone else to go do it. We had a bunch of civil servants that were doing this part of the job. Lockheed still built the launch abort system, but we built the rest to do it, right? And so we did it there. We did all the testing, did all our weight and CG, integration of the vehicle. We ended up actually completing this vehicle 6 months early and 2% under budget. So we delivered it, and we actually executed the flight test 6 months earlier than originally planned, which was really helpful for the agency. So here you can see us out at KSC, actually implementing the launch abort system with the crew module itself on top of the launch rocket.
Go.
And then we were able to execute the launch. And I don't know if you recognize the voice of the woman at the beginning of this to the voice of the woman calling the Morpheus call. It was the same woman, right, as the test conductor for those things. So we launched July 2nd, 2019 to execute this test. Again, 6 months earlier than planned. Sitting out there, being the test director for that entire test in a very different environment with a lot more eyes on us than what we had for Morpheus. Very different experience, but very rewarding. So we just had to get high enough to where we could actually execute the abort. We're targeting a specific region to execute the test. The most trying, right?
Pyros 1 and 2 discharge both sides. Pitching for pressure. Good control.
We had the same concept where all the same people who did the design and build of the vehicle were the flight controllers sitting on the consoles making all those calls as we were executing the flight test. So one of the things we did, because getting the data from here, I told you 11 miles of harness, 11 miles of wire, right? Because the data was the critical piece,
Reorientation.
not just the test itself, but the data we'd get back from it was so critical. And we were downlinking data as we flew. But we wanted to make sure that if we had a problem, we would collect as much data as we could. So while we're doing this as an in-house design, we actually invented an ejectable data recorder system.
Discharge both sides.
So watch as you see the capsule start to fall here.
Squid power enabled.
And you'll see a couple of orange things shoot out from it.
Started data rebroadcast.
But those were basically foam encapsulated thumb drives that we had to have plugs in, right? That the data could be transmitted into the thumb drive. And we had antennas
Second rebroadcast.
on the end of them. They were weighted so that they would hit the water, absolutely zero damage when they hit the water. They'd orient upright,
Launch data.
and they'd send emails through satellite back to us, their position in the water, so that we could actually track them. And we sent a boat out afterwards with a fishing net and scooped all 12 of them. We had 12 of them because we said, we're not going to have to make sure that it has to work. We're going to build 12 of them, so you're likely to get at least one, right? And so we ejected 12 of those things. We actually used a military chaff flare dispenser to shoot them out. And we modified that to have connectors run in to be able to collect the data. So all different ways to actually build out what we need, but we demonstrated what we needed to allow for safe crew flight. As a matter of fact, with that data, you saw the vehicle tumbling as it was coming down. They were actually able to collect enough data on the different coefficients as it was falling that we could narrow in the uncertainty of the models we had for the Orion capsule and actually save hundreds of kilograms of propellant that was there as a just in case, because we had never flown the Orion capsule before and didn't actually understand all the aerodynamic coefficients associated with it. So that's part of what we learned from tests like these. All right, so we use that to then get ready for the next step, right? So now we're going to go back to the moon. This is what we're trying to do. This is the part that you've heard a lot about before. So all of that was the lead up to how am I now working in this arena? Well, it's all that experience base before that gives me the opportunity to take it and work in an arena that says we're going to go back to the moon, right? And we need to be able to assess and adjudicate risk in the design and development of the things that we're building now. So I started with just responsibility for one module, building a single module, but it's all about the human lunar return at this point in time. It's getting back to the moon. We've been there before. It's not about doing the same thing again. It's about going back in a sustained way so we can have a sustained human presence in cislunar space and create a blueprint for us to be able to explore Mars and beyond, right? So in order to do that, we still have a bunch of capabilities, a bunch of technologies we need to continue to advance. And we do that, continue to do that through a variety of different programs that we have at NASA. You need spacesuits, right, that can be used both on orbit and on the surface of the moon. We haven't had spacesuits for surface use for many decades. So we need spacesuits to do that. We need a landing system, a human landing system, to get crew down to the surface. We need all our ground systems in Florida to be able to launch these things. We need a launch rocket that's human rated. That means that we're confident it's not going to explode, right? That we have all the right redundancies and capabilities built into it to make it human rated. We need surface mobility, and we need a space station. We need an orbital platform. Why do we need an orbital platform? This is just good imagery, so this can be playing in the background. Why do we need an orbital platform? You might have read, yes. Close. The orbital platform actually gives us access to the entire surface. Right? But go ahead. Did you have another thought? Okay, very good. Because there are other reasons too to have an orbital platform. Yeah. So you're right? The mass equation, the rocket equation with mass, right, is really unforgiving in getting to the moon. So as we talk here, you see the station we're talking about for cislunar space is much smaller than the International Space Station. Right? The mass is premium. So having a place where we can aggregate in cislunar space, where you can bring different capabilities, even potentially reuse capabilities, critically important to be able to have. Yes.
Longer mission times.
Absolutely, longer mission times, right? As part of that, is it just one time down to the surface per crewed mission, or can you go down multiple times? Can you have logistics stores up there in that orbiting platform, that station, that you can bring down for longer stays in one stay on the surface? Absolutely, right? Yes?
More resources for every mission, which reduces risk.
So absolutely, that's all right along the same line, exactly right, to be able to have those resources to reduce risk. It also gives you year-round science. Even when the crew is not there, you have access to science all year round, right? So how are we going to do this? We've already done Artemis 1. That was the imagery you just saw playing in the background. We're getting ready for Artemis 2. We've named the crew. We've got work to do to make sure that vehicle is ready to go. You see a lot of that in the news. I don't know how much you directly follow it, right? But we're going to make sure that we follow the hardware. We understand what the hardware's telling us. That's that risk-based decision making that I was talking about. Have to be able to understand the risks and figure out which ones are acceptable to take and which ones are not, right? But once we get that Artemis 2 and we demonstrate that Orion vehicle is good for supporting humans, then we move on to actually getting back to the surface. Artemis 3 right now is the one planned to land on the surface. So that's where Orion will dock directly to a Starship, and that Starship then becomes the lander. There's a variant of Starship that is a human lander version, and that's what will land on the surface. So that's Artemis 3. And then Artemis 4 and 5 will start bringing up additional capabilities for Gateway, and I'll talk about those here in a minute. So this little video montage will show you the sequence, right, that we will aggregate the space station in. So we'll launch the first two elements, the habitation logistics outpost and the power propulsion element. Those two, we launch them together. We bolt them together on the ground in Florida, and we'll launch them on a Falcon Heavy. The Halo is built by Northrop Grumman, and the PPE is built by Maxar Technologies, two completely different companies. We'll marry them together out in Florida and launch those. Artemis 4, Orion will bring it's called the IHAB, the International Habitat, that's built primarily by ESA. Orion will bring that out to Gateway and add it as part of the Gateway station. JAXA, Japan, is providing all of the environmental control and life support systems for that IHAB. So that forms the basis for Gateway. Artemis 5, the European refueling module will be brought out by Orion. That allows us to refuel the station multiple times in the future. It'll bring fuel with it, but it'll also have a docking capability on the back end so we can bring additional refuelers in the future. Because while we're building the station to last for at least 15 years, we expect to use it much longer than that, right? So that's kind of that design. And then in between those 4 and 5, we'll have a logistics vehicle that comes up and delivers an external arm, a robotic arm built by Canada. Similar to what we had on both Shuttle and ISS, this is Canada Arm 3 that's being designed and will be up there on this station. And then Artemis 6 will have an airlock. That airlock will be brought up again by Orion. That airlock is being designed and developed by the United Arab Emirates. The Mohammed bin Rashid Space Center in UAE is actually doing the development of the airlock for us. So they're our new international partner. They haven't been a part of what we've done before, but they are a new partner for NASA, which is actually tremendous. for us to be able to expand the partnership that we're working with across the globe. So this shows those partnerships. We are very much an international program. So I spend about 85% of my time on the road, literally, and all around the world. We can talk more about that. So the station. This again shows you kind of the difference in what we're doing for Gateway versus the International Space Station, right? ISS is now 24 years. We celebrated that the other day. 24 years of continued human presence on the ISS, which means anyone who's younger than 24 has never known a day where we haven't had humans living off of the Earth. 24 straight years, but it's crewed year-round. You have access regularly for cargo delivery, for cargo return, right? Crew change out. All of those things can happen regularly. So that logistics supply is there. And they have a number of EVAs that they do to maintain that station, right? So for Gateway, we're looking to be crewed about 30 days per year. So the other 11 months out of the year, it's all about autonomous operations of that vehicle. So I mentioned autonomous operations earlier. We're building out capabilities that we will continue to evolve that we'll need for Mars missions and beyond to demonstrate that autonomous operations capability on Gateway. Let's see, logistics, we'll only have one logistics supply vehicle per crewed mission. So we have to make sure, and we got everything we need that fits in that one logistics supply vehicle, plus whatever volume we happen to have on the station, which isn't a lot, right? So we'll have that, and EVA capability, we'll get that once we have the airlock up there, but we will only go do a spacewalk on Gateway if we have critical maintenance items that need to be maintained, right? That's the only time we'll do it. We're not gonna, we won't have the same number of EVAs like ISS does. We'll fly in a unique orbit. Some of you heard talks, I heard from Diane Davis, who talked to the Aerospace Engineering Department. She's brilliant, but she's one of the architects of the orbit that we'll fly in. It's called the Near Rectilinear Halo Orbit. It's actually a family of orbits that's basically balances gravity wells through the Earth, Moon, Sun system. And so it's not completely stable, but it's close enough that it requires limited fuel for us to maintain that orbit. So that's part of the design we do, but you can see all the reasons why we picked that orbit here, right? We talked about access to the entire surface. That's a key one. Talked about science. Being able to support comm. You see, most of the time we're actually quite a ways away from the South Pole. We get our close approach across the North Pole is about 1,000 kilometers, but we're 70,000 kilometers away, right, at apogee. But that means most of the time we have really good line of sight to the South Pole, so pretty good comm coverage, for example, from there. Our orbit is about 6.5 days to do a complete orbit there around the moon. All right, I mentioned the initial capability. We're launching with both the Halo and PPE together from KSC, so I'll talk a little bit more about that here real quick, because we're making a ton of progress in those. So this is not just PowerPoint engineering. All right, we have the vehicle making substantial progress. This is the power and propulsion element. It's largely coming together. So in a few months, we'll actually have the vehicle completely assembled and get into environmental testing for that vehicle. So it's making tremendous progress. The Habitation Logistics Outpost is currently in Italy. We finished all the primary structure work and testing that we've done. It's now being outfitted with its secondary structure, and it will be shipped early next year to Arizona, to the Northrop Grumman facility there, where it will be have all its assembly and integration done with all of the different piece parts that it needs inside that vehicle. So in the meantime, all of those parts are being built as well and then being shipped out there when they're ready. So you have all the different everything from power distribution systems, right, to environmental control systems, ducting, fans, all of the different pieces, all your computers, all your network management, all that stuff is going on in parallel and will be integrated into that vehicle. And then all of the other vehicles are making progress as well. So the International Habitat is a little bit behind those other two on purpose. It's flying later than those will. I didn't mention on the PPE slide, I'll maybe go back to that one, if it'll let me. Yeah, we don't have a good picture of the thrusters on this one, but we're using solar electric propulsion. Right? It'll be the most powerful SEP engines that have ever been flown that will be here. This is going to be a very large vehicle that we launch. It's going to take us about a year using those SEP engines to actually spiral out into cislunar orbit once we launch. So we've got about a year before we can have Orion bring that IHAB to us. And then we'll have all the science that we're able to do. So we will launch with payloads on the vehicle. So we'll start science from day one. Specifically, we'll get space weather, we get radiation. Those are the experiments we're launching with initially. But when we get out, because we got to transfer through the Van Allen belts to get out to cislunar space, so that's going to be incredible data for us. But once we get out there, we're going to be outside of the Earth's magnetosphere for most of our orbit. There's actually a tail where we cross through, but for most of our orbit, we're outside of that. So we'll actually get really good deep space radiation and space weather data once we're there. And then it opens you up to all sorts of other types of science once we're on location. And that's where we'll have everything from physiology, all sorts of medical and human interaction types of science, heliophysics, variety of different types of science we'll be able to pursue once we get Gateway out there. But it all comes back to getting ready to launch. So this talks about us getting ready for Artemis 2.
Something that we dreamed about into reality.
It sent a message really to the world that we have laid the foundation for a generational rocket.
How many times in your career do you get to be a part of first?
At liftoff of Artemis 1, we rise together back to the moon and beyond.
For Artemis, this is just the starting point.
Ladies and gentlemen, your Artemis 2 crew.
Thank you to the NASA workforce. Thank you to our industry partners. Everyone in Europe is working for this. America has made a very deliberate choice to curate a global team, and we are going to the moon together.
We need to celebrate this moment in human history. It is the next step on the journey that gets humanity to Mars.
Am I excited? Absolutely.
We're going to test out the vehicle's ability to conduct rendezvous maneuvers, the crew's ability to actually fly Orion manually, and most importantly, we're going to test the environmental control system. We got humans on board. We got to keep them safe. We got to keep them breathing. And then we're going to have them come back at that high-speed entry at 32 times the speed of sound and make sure that they can survive this for future missions.
And so we have new launch commit criteria, we have changes to our procedure, changes to our timelines. We have new systems for crew, we have new systems for the capsule, we have an emergency egress system.
By building incrementally these capabilities, improving these capabilities that we have, we will be able to live on the moon and be able to perform science for deep space exploration.
I am ready for Artemis 2. The SLS team is ready for Artemis 2.
We are ready for Artemis 2.
We are ready.
We are ready.
All right, I'm ready. Let's go.
It's a great job to have. Really enjoy being able to work the different types of challenges and problems that we work day to day. So I've gone through all of that just to give you a feel for the variety of things that I've been fortunate to work in my career. And fortunate is a key part of it, right? It does takes luck, but it takes perseverance. It takes diligence. It takes figuring out what it is you enjoy and striving to achieve that. So I'd make no bones about I'm very lucky to do the job that I get to do. Very, very lucky. But everyone has that opportunity. Every one of you in here can do the same for whatever it is that drives you. And you have to figure that out. Don't let anyone else tell you what you should do. You figure out what you want to do, and then you got to go get it, right? And when that one door closes, realize that there's a window. Go find another path. Several times in my career, I had to make choices of what I wanted to go do and what I didn't want to go do. You don't always have to say yes when you're offered something. You don't always have to say yes. Saying no is okay. Figure out what it is that you want to do and pursue that. For me, I had to figure out what my weaknesses were as I went along in my career. Figure out what I didn't know, what I didn't have experience in, and then go try to get that experience. The only reason I have the job I have today is because I took risks to do things that I otherwise would not want to do. They were not the things that I thought I wanted to do at that point in time. But I knew I needed the experience in them to give me the opportunity to do this type of job. Never would have imagined, actually, that I get to do this exact job. But this type of thing is something that I did absolutely have interest in. And so just making decisions to advance my capabilities, my experience base is really what it was, right? Being able to figure out how to handle the different situations. That's what it was all about. So anyway, I'll leave you with that as you have future decisions for yourselves. So I'll stop there, but then I'm open to questions and answers. I know I really like what I do, so I actually end up talking long. I apologize for that. So I know I took a long time walking through all of that, but I'm happy to answer questions if anyone has any. Yes?
When do you expect data to be operating?
So good question. We are, you saw kind of where we are with those first elements. We're a couple years away from being able to launch because we have to finish all that outfitting of both of those modules, do all of their separate environmental testing of them, and then bring them together down in Florida and make sure they actually work together before we put them on the launch vehicle. So we're a good couple years away from that launch. And again, once we launch, it's another year for them to get out into cislunar space. So we're at least 3-ish years from being able to support an Artemis mission. Okay? Yes?
Where did the name Morpheus come from? What's the namesake for that project?
Morpheus, great question. Morpheus was the god of dreams and dreamers. So that was actually the reason we went with the name Morpheus. Anyone been to Mardi Gras? So there's actually a Morpheus crew that runs in New Orleans. So their parade is usually a week before Mardi Gras. Had one of their crew members come through and do a tour at one point in time. They actually ended up inviting me to be the whatever the title is for their parade. What's that? What's the title? I can't remember. Anyway, so they asked me to go do that. Of course, NASA legal said, yeah, no, no, you're not going to go do that for a Mardi Gras parade. But still, yeah. So it's God of dreams and dreamers. Yes.
What technologies need to be developed for the performance to be really so cool?
So really good question. The flights we're talking about doing now limit crew time in cislunar space to the 30-ish days, right? So you start right off the bat, radiation. How are we protecting crew from radiation? Because when you go to Mars, right, you're facing radiation the entire time, and there's no 30-day going to Mars, right? So you're talking years. So how are we going to keep crew safe from radiation? That's an example, right? Regenerative closed loop life support is another one. You're not going to have logistics supply. So we fly water, for example, up to space station all the time. And space station recirculates water. But you still only get a percentage of that back. Right? So they're pretty efficient. It's 90-something%. And yet they still have to launch water to resupply regularly to the ISS. For us on Gateway, we're not going to have regenerative life support because we're only there for 30 days at a time. So we're not going to start with that. We're scarring in case we develop that in the future, right? But we don't have the logistics supply chain to bring water for longer stays yet, right? We'll bring enough water for the specific mission that's defined. Again, you go to Mars, you can't have a 98% effective reclamation of water. You'll still run out of water, right? You can't bring enough with you. So how do you improve your reclamation of water? Right? What can you do? Food development, right? How are you going to deal with any diseases in a closed space like that? Right? What are you going to do with those things? So that's just the human side. Autonomous operations is another really key aspect. How are you going to actually have the vehicle fly itself for that long? How are you going to do maintenance when you don't have spares? What type of 3D printing technology are you going to bring with what materials to enable you to do what? Right? How are you going to advance those technologies? How are you going to figure out all those systems that you're going to make those risk balance decisions on? Here's what you're going to protect for, and here's what you're not going to protect for. So there's a couple things. Yes, absolutely. Yes.
You said for the launchable you used email to figure out where it was. Why did you use email over like RF or something else?
So simply we had access to the satellite constellation early. I'm sorry, I'm just not remembering which satellite but we had access to the satellite constellation, but it was low data rate, right? So fundamentally for us with that EDR, that ejectable data recorder, it was all about low data rate. Just a simple signal. You didn't need a lot of power because we had to have obviously battery in there for that as well. So you didn't need a lot of power. Just something that would be able to transmit, and that allowed us to, and we didn't need anything faster, right? Because every 5 minutes, it was really easy to track. Over 20 minutes, you get 4 data points, and you know where the current's going, and they're all traveling the same direction, and it's pretty easy to come behind them. So we didn't need anything more robust than that. That was the primary driver, right? We just went as simple as we could. Make the simple solution the right solution, right? And make sure I didn't miss anybody. Go ahead.
What kind of payloads are you guys launching for the first?
So we've got 3 different payloads. We've got one's called Hermes. Goddard Space Flight Center is building that. That's a radiation space weather type payload that'll be on Halo. It'll be on the outside of Halo. Have different view out into space as we're flying through the Van Allen belts and then out in orbit as well. So it's got a set of instruments on it. There's another one called Ursa that Europe is building. It's a complementary set of instruments, so also studying radiation and space weather, but it'll fly on the power propulsion element side, also outside. And then we have an internal radiation monitoring suite that's in a locker inside the vehicle, and it's really trying to measure the difference from those that are external to the vehicle to what gets through internally, so we have a better understanding of what crew is going to be dealing with inside the vehicle. So those are the 3 that we're launching with initially. Okay? Yes?
You mentioned a few times autonomous landing systems and those
Yep.
sorts of things, but you also mentioned bringing surface assets closer together. There's a risk with plume and with kick-up in general. Is there any discussion on how to mitigate that while you start bringing those ideas together to create sort of colonies or surface habitat areas together?
Yeah, absolutely. So even studying that with our lunar landings. So do you know the CLIPS program? Have you heard of CLIPS? Right. So the Commercial Lunar Payload Services, Intuitive Machines, just landed back in February, I think it was January, February, right? First soft landing of a U.S. lander in 50 years. That Intuitive Machines company, several of my Morpheus team went and started that company. So they actually used the same navigation algorithms, the same LOX methane propulsion, the same engine designer, right? So works at that company now. But they are studying, as are a number of folks, studying plume impingement and trying to understand what the plume fields actually are going to be, both lunar surface as well as then other planetary, where atmospheres are going to be different, and so your responses are going to be different, right? So those are all real assessments. They are real concerns. So it might be that, you know, when you actually come to land on Mars, you're not actually going to land where you end up, right? Maybe you're 10 meters away or 20 meters away, but you're not hundreds of meters away. So you're still going to have to think through mobility, right? Do I need to move that asset once it lands? Or do I have some other connecting capability that needs to exist, some type of tunneling system that ties the two together? You still have to think through all of those things, but you've got to be close enough to where you can actually go address that, right? And so that's part of the driver, is at least being close enough you can put it where you want. There's other technologies we're going to have to go pursue that include surface mobility, right? And so we're starting that on the moon. We'll expand what we learn out to Mars. Yes?
Was NASA's mission for going to the moon and then Mars different from private companies like SpaceX?
So the missions, yeah, I would say right now, the Starship development for SpaceX, one, we work very, very well integrated with them. So the Starship development is happening from a landing perspective through NASA. So that they're on contract with NASA to do human landing to the lunar surface. So that's where that development is coming. We're all working together to make that happen. But absolutely, private companies have their own pursuits as well, right? So there's not a requirement for private companies to be 100% aligned with what the government is doing. The government, right? We're definitely, from a government perspective, we have specific pursuits that we're trying to do to advance capabilities on behalf of humanity and behalf of the country, right? A lot of what we do ends up coming back into the country, coming back to Earth to improve life here on Earth. That's happened ever since we started exploring, right, in space. So different types of things we learn. There are so many examples of technologies that we rely on today in our everyday life. It's all because of space exploration. We'll continue to do those things by exploring. And as a government entity, there's places where we can go pursue risky endeavors that private companies would not want to do because the return on investment is not necessarily, doesn't close the business case, right? Fundamentally. And that's the way it's always been. Government started air travel, right? That was all government driven until it became mature enough that private companies could actually take it and make it their own business case. So that's what we're talking about here. We talk about a low Earth orbit economy where you have a privately owned space station, right? So they'll have their own drivers, their own requirements, the things that they need for that space station, right? But they've got to make their own business case to make that work, right? And we will use whatever capabilities that are there. Same thing can be said for launch vehicles you see all across the globe, right? Launch vehicles, it's all their business case. So we build our own launcher to make it human rated because most other people are not building human rated launchers, right? They buy insurance to deal with a failure. We can't have a failure at that point in time. So part of that learning risk and being able to crash on an R&D is because that's when you want to actually have those types of problems and figure out where you're pushing the envelope too far so that you're not doing that when you've got people on board, right? So that's a little bit of the difference, but we definitely work together. It's not a competition, right? We work together with private industry, always have, to make things happen. Other questions? Yes?
Do you expect the sale of potential sale of cloned space to affect the gateway missions?
I'd say probably not. Under those types of things, there's been maneuvers through the aerospace industry for years, and there always are. There's mergers, there's dissolutions, right? Those things happen at a variety of levels. So sometimes it's large companies like Boeing, sometimes it's conglomerates, sometimes they join in joint ventures, but sometimes it's also small companies, and they get bought up by some other company, right? And then you have different aspects to pursue there. Orbital Sciences was its own launch capability initially, and they did the cargo supply for the ISS initially. Then they merged with ATK, and then Northrop Grumman bought them, right? So that type of corporate maneuvering happens all the time, right? So we just work through that environment. Yes.
With the focus on making the vehicles viable for humans, especially the long-term trips, how do you deal with the loss of muscle mass and bone density?
Great question, and that's one of the things that we spend a lot of time working on. Exercise is one of the biggest aspects, right? Nutrition is also plays into that, but we put a lot of emphasis on what type of exercise devices we have. That's not as simple as saying, hey, go jump rope, right? Not only is that tough, because jumping actually does exercise muscles differently than running, for example, right? So there's different benefits that you could say you'd have from something like that. Or using rowing or cycling, right? They all different modalities that help the body condition differently, but they all also interact with the spacecraft itself. So for example, when Orion docks to a radial port on Gateway, and it's docked there, and it has an exercise device, it's called a flywheel in Orion, right? And it can have a kind of a rowing modality or a little bit of a cycling modality to it. But when it's sitting there docked to Gateway, if crew exercises there, it could actually break the solar arrays on PPE because of the vibration cascade through the structure all the way to PPE. They actually would augment, right? You'd actually have modes that overlay where you could end up breaking the solar arrays. So how we design vibration isolation into those things makes a difference, right? What modalities and what you're able to actually design vibration isolation into makes a difference. So it's not just what does the human need, but also what can you deliver that enables the crew to stay conditioned. Right? But that's the primary means, is still exercise. I'm sorry, she had a question back there. Yes. I'm sorry, I cannot hear you. So good question, and there's solar electric propulsion, right? So they're not higher thrust, they're actually low thrust, right? But they're high power. So these are 12 kilowatt powered engines. And so we can test those. We can actually test them in a chamber up at Glenn Research Center. You can actually use a 12 kilowatt power pack, and you can drive those thrusters and demonstrate their performance. Right. So actually we have that capability to test it on the ground. No one's ever flown one that powerful before. Yep. There was another question. Yes.
Has artificial intelligence made a significant change of how you used to do things and how you do things?
Good question. Not yet. Right? So there is a lot of conversation about artificial intelligence. There's a lot of thought. NASA's putting thought into what we do with artificial intelligence, where we might incorporate it, where we might not. Autonomous operations, I told you, right, is a key focus. We're actually doing all our software development for the autonomous operations in-house at NASA, so we're doing that work. How much it is its own form of AI, right? But it's not really what you hear about anymore. So how much we evolve it, how much we incorporate a true AI engine is still TBD, right? We haven't made any decisions on that, where we go with that yet. Okay, future evolution. Yes.
Is NASA using or planning to use like nuclear propulsion for anything?
That's also a good question, right? So there are aspects of pursuing nuclear propulsion. There are different projects that are out there. They're early design prototype type stages, right? It's something that's been talked about, different forms of nuclear thermal, right? Different types of nuclear propulsion. There's a large group that believe that's where you need to go in order to actually make Mars missions or beyond much more viable to execute. And so there is absolutely work in that, but it's right now more at that research and development stage, like where Morpheus was, right? Rather than, hey, we're ready to go pursue a system.
What do you see like the timeline for that for actually coming into play?
It's not my field, so it's hard for me to actually say. I know we've got a lot of people putting effort into trying to advance that capability, but I don't have a timeline for you. Anything else? Cut me off?
Yeah.
Sorry.
Yeah. So, well, 8:23. I know some of you are probably to leave, so we're just gonna sort of call it here.
I can stay for a few more minutes. Yeah, absolutely, and
Okay.
answer some one-on-one questions.
I think we can also answer some questions about.
Yeah, so I'll be here for a few additional minutes as well. So just want to give y'all the opportunity to leave if you need to leave. Stick around if you have questions for officers. Anything